Hey guys, welcome back. Today, day 11, we're talking about waves. All right, so let's talk about the characteristics of waves. The first thing we got is lambda. All right, that's lambda, which is the wavelength. So we use a Greek L, but it's the wavelength, and that's the distance between closest identical points. All right. Meters, centimeters, picometers, nanometers, it can be any type of meter. All right, any type of meter. That's the distance. Right, and so when we look at wave, it looks a lot like y equals like sine x. That's a wavelength, right? So this point here, that point here. Now, this wave technically keeps going, right? It'll keep going. So technically, if I had this point here and this point here, where that would cross the x-axis, that'd be a wavelength as well. Next up is frequency, nu. All right. This is frequency. And this is the rate at which waves, if I could spell, pass a certain point. Right? Second person, -1 or 1 over seconds, hertz. Right, so those are the waves. That's a wave. Now, there's two main types of transverse waves we're going to do. We're not going to talk about compression waves. Sound waves. Sound waves are compression waves where the air is compressed and expands. We're not going to worry about those right now. We're going to worry about transverse waves. And we're going to have traveling waves and stationary waves. Right? And when we talk about stationary waves, think about a violin string, guitar string, whatever string instrument, if you ever used one, played with one, whatnot. All right, and it's a one-dimensional, and so the frequency, right? If the frequency is just one wave, so over on the bottom here, if I pluck the string, if I pull the string up, right, then it'll come down. Oh, that's horrible. Let's try it better. There we go. Right? And what happens is that this wave, right, the string will come up and down. And it looks like it's vibrating back and forth here, but the whole string goes up and then down, and it vibrates. But it has to vibrate, right, where the whole length, the length here, the length has to be, all right, wavelength over, right, it's n. Well, n's a quantum number, so n is like 1, half a wavelength here. So this is half a wavelength. All right? We can do it where it comes up. Oh, it went straight. It comes up, something like that, and then the mirror image, right, where you have 2 wavelengths. Or it could be even 3 wavelengths. I'm going to try to draw this one. Something like that. And a good analogy of this, for those of you who like to work out, and you've seen people do the ropes, or they call them just the ropes, or the battle ropes, or whatever, and it's a shoulder exercise where you're there and you pick the ropes up and down against the wall. And it's one of those exercises you can't cheat on, because you have to have this situation occur where it's either a whole or half of a wavelength going on with the rope. You can't have you can't just do it any speed you want, and usually you got to get going pretty fast to make it work. All right, it's one of those exercises where cheating does not happen. All right, and this leads us to these things called quantum numbers. All right, and why are we talking about waves? Well, we're going to get to here a little bit later on that the electron is going to be treated as a wave. But right now we're doing more waves, and why we're treating it as a wave, and it's unclear. Quantum mechanics, my professor in grad school says the first time you get quantum mechanics, you don't understand it. Then you take a higher level quantum mechanics and you think you understand it, and then you take it a third time and you really have no idea what you're doing. And that's kind of how quantum mechanics is. It's very abstract, extremely abstract. But we're talking basic characteristics of waves, all right? And then we're going to talk basic characteristics of particles, and then we're going to go on from there, all right? And so this quantum number comes into the Schrodinger equation, which we'll get to, and these are whole numbers that represent a physical characteristic or, physical characteristic of the wave. Okay, and because these are one-dimensional, right? These are they have one quantum number. When there's two dimensionals, you have two quantum numbers. If it's three-dimensional, you have three quantum numbers, right? And so the frequency is one frequency, times the frequency, three times the frequency. And again, if this is not that interesting to you, that's okay. We're just going to go on to the meat and potatoes of it, right? If you're interested in waves, there's a lot of cool stuff you can do with it. All right, and then we're going to dive into we're going to skip this, and we're going to go into this next, and then we're going to go back up to Heisenberg. All right, so diffraction. So another wave phenomenon versus a particle phenomenon, right? So we got wave and particle. All right, and so the wave and particle going through slits, right? We call it diffraction, and waves can come through, right? This slit here, and they get bigger, 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 and bigger and bigger, right? Okay, and the reason we have a light bulb here, right? The light's on. I can be standing here until the light's on, right? So if I am standing here or you're standing here, you can tell somebody let the light on, right? However, if I'm standing here and somebody's trying to kick the soccer ball at you, right? The soccer ball, even if it curves a little bit, it's going straight through. The football, it's going straight through. They cannot, right? This does not happen. Right? Boom, it stops. So particle behavior cannot go around corners. Light can. And that leads to diffraction. What is this diffraction? Well, you see right here, these waves are interacting with each other as they come through, right? The waves break up and then they interact. Okay? And this leads us to a diffraction pattern. Okay? And so what happens is, if you were to look at this screen, you would have some bright spots on the screen, and in between would be dark. All right? And so if I could look at the face of that screen, if you could look at the face, you would see like very bright lights. It looks like this. So it'd be the bright yellow would be the lights that you would see where the waves interfere constructively, or the waves get together and get bigger. And then you would have dark spots. I think I can do dark. Can I do black? I can. You'd have dark spots in between. All right, so you'd have dark in between. So it goes from light to dark, light to dark. All right, and what that diffraction pattern does, right? Okay, you got constructive and destructive interference. Where constructive interference is the waves add together, right? It's kind of like sine x plus sine x. Destructive is the waves subtract. Sine x minus sine x. Okay. All right. So that's wave particle behavior versus particle behavior, right? And so we kind of understand particle behavior very well. Wave, now if you have a boat, you go out on boats a lot, and especially where I live, where there's the intercoastal waterway and the ocean, you see a lot of water waves and how they interact. It's the same principles. All right, so we're going to come back up here and talk about Heisenberg. And so at the same time all this is going on, a guy named Heisenberg's actually trying to figure out where the electron is in the atom, right? We've already talked about most of the space, right, is due to the electron, all right? And so where is the electron in all this space relative to its size, right? A good analogy would be like if you were at a football stadium, right, a big football stadium at a university or NFL or even a soccer, stadium, huge stadium, more than 50,000 people. Right? If it's just you in that stadium, they're like, where are you is kind of hard to find, right? Because there could be a lot of space in there for where you are, right? It's like, oh, I'm at this stadium. Okay, that doesn't narrow it down that well. Like, where are you? And are you staying in the same spot? Probably not. Maybe you're moving around. So it would be very hard to find where you are. So Heisenberg's like, well, let's try to find out where the electron is, right? And so, as you guys know, in order to observe something, you have to shine light on it, right? Right? Requires shining light or other electromagnetic radiation. X-ray. I think I have a broken bone. Hopefully you don't. Hopefully I don't. But let's say we have a broken bone. Oh, we shine some light on it. Oh, yep, it's X-ray light, and right, you do this with your dental X-rays, making sure, right, we can use that to see, right? And so radar, right, radio waves, radar. It's hard to see objects smaller than a meter. Radar is very important, right? I mean, we use a lot of planes in the air. It's good to have radar. Microwaves, actually a lot of radar now. Some of them use microwaves. The military, uses that, and they can see more. Visible, all right? So visible light, we can see micrometers, all right? Because the wavelength of the light has to be at least the same size as the object. So since we use the visible, I mean, think about it. Whatever you're looking at, all the things that we use, touching, right? Way bigger than micrometers, right? Many times, sometimes 1,000 times, 10,000 times, 100,000 times bigger than a micrometer. So we have very good precision on where something is. I mean, think about it. People can hit a baseball, right? That's moving 90 miles an hour. That's pretty impressive, right? Because of the precision, because our light we're using is so much bigger than the object, or so much smaller than the object we're looking at. So the nanometer wavelengths in the baseball is, right, many centimeters long. We very good precision, right? And so the delta x, that's the uncertainty in position where the object is in direction x, right? So if I'm going to grab a coffee cup or a drink on the right in the x direction, I know very certainly where it is because I have two eyes and I can see exactly where my beverage is, right? Or your pencil or whatever. The smaller the wavelength, the greater the precision. So because we use so small wavelengths, we have very good precision where our drink is. So the question becomes, why not use a very, very, very small wavelength to observe the electron, right? Because how big is the electron? Well, we don't really know, but let's just say it's extremely small. Well, there's light that's extremely small. We can do that, right? Okay, and the problem because, right, if I have an electron here hanging out, there's my electron. We're pretend it's a sphere. There's my electron. If I bring in some very high energy light to hit it, right? So lambda is very small. Very small. All right? So if C equals lambda nu, if lambda is very small, very, very small, nu is very, very big. And this photon comes in with energy equals E equals h nu. So if nu is very big, energy is very big. Now, you can try this experiment where if your lights are off, you can turn the light on and see if anything happens to you. And chances are no, right? Maybe your eyes momentarily adjust. This electron, right, has a mass of 9.11 times 10 to negative 31 kilograms. So when this photon hits this electron, right, it's a collision, and there is going to be a transfer of momentum. Right? There is a collision. This is now delta x. Right? And there is a transfer of momentum. All right? So, the problem we have is small wavelength equals large frequency equals large energy. All right. So there's a transfer of momentum and there's a change in position, right? It's trying to, like if you were trying to play pool, a good analogy. You're playing pool, you have the cue ball, and you got to hit any ball. It doesn't matter what ball it is. I'm not a billiards expert. I'm trying to hit a ball, right? The problem is it's completely dark and you can't see where the ball is. So you hit the cue ball, boom, you hit the ball, right? But then because you hit the ball, now the ball moved, right? And so then you got to go try to figure out where the ball is again from the same starting point too. Like you're not moving around with your cue ball. You have to stay at the same spot. So it makes it very difficult, right, to find out where this electron is, right? And so what Heisenberg basically says, right, is that we cannot know both the momentum and the position of the electron at the same time. So delta x multiplied by m delta v is greater than or equal to h divided by 4 pi. All right, and so what do we have here? We have the uncertainty in position in meters. We got m for mass. We have the uncertainty in velocity. And you have Planck's constant here. All right, and then 4 pi. Now, mass. Big important with the mass has to be in kilograms because this is joules, right? Which is Newton meters, which is kilograms, meter squared, second squared. So we got to be in kilograms. But that is Heisenberg's uncertainty principle. Now, fortunately, h is a very tiny number. So this is only evident in very, very tiny particles and subatomic particles like electrons. All right. So, for example, this example. So this is from a physics book. Hydrogen is an electron. Assume that the electron of hydrogen is traveling at 2.19 times 10 to the 6 meters per second. Assume the atom is a sphere with a radius of 53 picometers. How many times in a minute does the electron travel around the hydrogen atom? All right, so we have 53 picometers here, which is the same thing as 53 times 10 to negative 12 meters. And you have an electron here, and it's just, we're going to assume it's traveling in a circle, 2.19 times 10 to the 6 meters per second. All right, how many times a minute does this happen? Well, basic physics, distance is velocity or speed times time. So we have 53 times 10 to negative 12 meters equals 2.19 times 10 to the 6 meters per second times the time. So our time would be 2.4 times 10 to the negative 17 seconds. That's how long it takes for the electron to go around the 53, picometer radius. Well, that would be the period. I want to know what 1 over t is, right? So 1 over 2.4 times 10 to the negative 17, that would happen to be 4.1 times 10 to the 16. 1 over seconds. Well, I asked for a minute, so 4.1 times 10 to the 16, 1 over seconds, times 60 seconds and 1 minute, gives me 2.5 times 10 to the 18 RPM. That's a lot. Just so we know, if you have the helicopters that fly over, right, their rotors are typically between 400 and 500 RPM. So that's what the rotors of a helicopter typically are, right? The plane props go around 2,500 to 3,000 RPM. Jet engines, their turbines are about 15,000 RPM. So that's 1.5 times 10 to the 4th. This is 3 times 10 to the 3rd, 5 times 10 to the 2nd. And so we probably would never try to, you might have done this as a kid with the ceiling fan, where the ceiling fan's going, you try to put your hand up and below the ceiling fan, right, while it's moving, right? And it hits you, of course, and it just slows down a little bit, and you notice that it hits you, and then it keeps going. You would never do that with a helicopter rotor or a plane prop or a jet engine. And you see how fast they're going, right? However, like the plane props, World War II planes, a lot of times their machine guns fired through the bullets went through the plane props because they were timed, and the bullet could actually do that. It was flying fast enough. The problem with this is that this electron, right? This electron is going so fast around, right? It's almost a complete circle, right? And it's in 360 degrees. It's just the electron everywhere, right? And so it might seem like it's everywhere at once. It's not, but for our point of view, it's everywhere at once. It's really weird. All right? What does this all mean? All right? What does all this mean? So the electron is not static. Electron's moving around this, but it's moving around ridiculously fast. Okay? All right? And let's write the key points down. We know that waves and particles move and interact differently. Right? The other thing that we have learned is that electrons, right, can exhibit both wave and particle behavior. Okay? So electrons can exhibit wave behavior, and electrons can exhibit particle behavior, which is really weird. All right? And the electrons are observed exhibiting wave behavior in their diffraction. So they make a diffraction pattern. Now, this is what's really weird. Note the interference pattern of electrons is not caused by pairs of electrons interfering with one another, but rather by single electrons interfering with themselves. So electrons interfere with themselves in the diffraction, which is really weird. But again, we talked about this in the day 10 video, where Thomson and others did this experiment where they diffracted electrons. And so we have a Nobel Prize for the electron being a wave and a Nobel Prize for electron being a particle. And so the question is, which is it? Right? That's the question. Which is the electron? Is it a wave? Is it a particle? And of course, the answer is it's neither, right? It's neither, right? I believe we mentioned that. It's neither a wave or a particle. It's a quantum object, all right? And so right now we are in this weird spot. What's coming next, right, is day 12, quantum mechanics. And in that, we are going to break down like what we do with this, right? So, okay, we have this electron. It's kind of like everywhere at once. We